Okay, so chapter 10, linear kinematics of human movement. Remember in section dynamics, we did some kinematics, but the kinematics that you did were general and linear most of the time. Why do we have the class biomechanics after the section dynamics? Is that because I would like to focus on the kinematics of human motion and sport. So we will look at linear kinematics and then we'll do the angular kinematics. Why do you think linear kinematics is important for biomechanics? Even though that everything is moving in the body with angles. If you're playing sports, you're translating force to object. For example, playing golf, you're going to translate your muscle forces and transfer them into the ball that is moving, right? And that thing is going to be moving linearly, and that's why we'd like to study this. So what are the interrelationship among kinematic variables? We need to learn about these variables. What are the kinematic variables you can think of? Position, velocity, acceleration. And how to distinguish between average and instantaneous quantities. That's another important concept. And what are the effect of factors governing projectile trajectory? There are a lot of projectile examples in sports that you need to get into. How to solve problems related to linear kinematics, that's what we're going to be solving today. We will discuss the relationships, associate linear kinematics quantity with the units, identify and describe the effect of factors governing projectile theory. These are objectives, and explain why the horizontal and vertical components of a projectile motion are analyzed separately. We're going to do the analysis today and distinguish between average and instantaneous quantities, and then select and use appropriate equations to solve problems. Now, if we do projectile, is it a constant acceleration problem or no? What acceleration acts when we have projectile? Only gravity, that's constant. Let's start with this. The motion of a projectile can be treated as a two rectilinear motion, one in the horizontal axis, one on the vertical axis. And we are going to use the constant acceleration equations. The first one, v final equals the velocity final equals velocity initial plus the acceleration multiplied by time. Those are the constant acceleration equations of motion. The second one, the distance, final distance, equal initial velocity multiplied by time plus half acceleration multiplied by time square, and the final velocity square equals the initial velocity square plus 2 multiplied by the acceleration multiplied by d. Now, what is the only acceleration that acts during projectile? It's just gravitational acceleration. How much is the gravitational acceleration? 9.81 meters per second square. If we are doing projectile, is this positive or negative? Negative, because it's pulling down. Now, here's what we want to do. Any projectile problem needs to be broken down into two different problems, one in the x-axis and one in the y-axis. So the velocities will be in x and y, initial velocity and final velocities. And then you can solve. The distances also need to be x and y distances. In the x-axis, in the horizontal motion, acceleration equals to 0. There is nothing pulling your object in the horizontal axis. Only AY is the 9.81. The velocity in the horizontal axis remains constant, so V final in the x-axis should be V initial in the x-axis. And the position in the x direction can be measured by x final equals x initial plus Vt. The vertical motion, we have acceleration AY equals minus G, and we have these equations of motion for constant acceleration. V final equals V initial in GT in the y-axis, and the distance, final distance, equals initial y distance plus the velocity in the y initial time minus half gt square, and the Vy square, the final velocity at y, equals the initial velocity at y square minus 2g with the differences between the y distances. And for any given problem, only two of these three equations required in the y-axis because they are not independent. They're dependent variables. So you need only two. And you will select how to do these two. Okay, guys. So let's do an example. And let's refresh our information about projectile analysis. This should be easy, but I'm going to do it with you, and I want you to help me how to do that. If I gave you the velocity VA is 10 meters per second. So someone is kicking the soccer ball. We have a velocity of 10 meters per second, 10 meters per second, and the angle is 30 degrees. And we would like to find the horizontal distance it travels and the velocity at C, at point C. Now this is important because in your second exam we will have these problems. So what is the first step you need to do? Step 1, you need to apply the kinematic relations in the X and Y direction separately.
I was just wondering if this is one of those problems where you want us to take pictures and then
No. We're going to do other example. I want to explain it first once. We'll do it together, and then we'll do that thing later on. But it's good to practice to work together. I just want to make sure that we are on the same page. So, how would you do this? The first step is, look at this. I have a projectile force. I need to make sure that I have something in the x-axis and something in the y-axis, right? So here's what I'm going to do. I'm going to split this in halves, and I'm going to say that's in the x, that's the horizontal, and that's the y. We good? Right? Now, in the horizontal, I need to find the velocity, the initial velocity in the x-axis and the initial velocity in the y-axis. So you have a v equals 10. So I need to break this into 1 in the x-axis and 1 in the y-axis. Does that make sense? So the Vx initial, how much is that? The value of the V is 10, correct? And I have an angle of 30. So that's going to be 10 cosine or sine? Cosine because it is between the two, right? So that's cosine multiplied by cosine 30. Done. That's your velocity. Now remember, the Vx0 should always be the same as Vx final because we don't have acceleration. So velocity in the x-axis, initial and final should be the same. We good? Now, Vy initial, how much is that? 10 sine 30. Correct? Right? These are the two here. Now, you need to look at your equations of motion. So I have the initial velocities here. So let's say x in the x final should equals x initial plus vt. Remember? X final, the position, equals x initial, which is 0. If I assume that this is the 0 point, this is my 0, 0 point. I'm going to start from this point, right? So that's equals x0 plus vt.
What's the subscript you have on the x, like that, where it says x of whatever that is?
This.
X? Well, no, like over like the second equation you just wrote, the x of
final distance equals initial distance 0.
Okay.
Plus vx0 time.
Okay.
And that's vx0. Because the vx is the same. You know, the vx here, same thing as vx here. Vx final and vx initial, they're the same. This one is equal to that one. So at the final, we use that one. Now, so what happened here is x final, which is the distance. So this is the x final. See? This is the distance of x final. How much in the x-axis I'm going to move equals x0 is 0, right? We don't have, I'm starting from this point. Plus Vx0 is, how much is 10 cosine 30? Do you have a calculator? 10 multiplied by cosine 30.
Yeah, 8.66.
So 8.66 t, right? That's the time it's going to take the ball to reach the other point. Now, I don't want the 0, so x final equals 8.66 multiplied by t, correct? How many unknowns do I have? This is my first equation of motion. 2, right? I have t and x final. I don't know x final. We don't know how far that went, and also time. So I need to rely on which one? On the y. So I will say that the y final equals v y t, right, minus half g t squared, y0. Now, this is y0, v y0, and the one that we need is this one, vy final, right? The y final, this is my initial. What do you think the y final here is? 0. So the y final is 0. So that's going to be 0 equals 10. How much is 10 sine 30? Exactly 5.
Yes.
Just half. Now, multiplied by t minus half. How much is half of 9.81? 491 t squared. Look at this. This is my second equation of motion. How many unknowns do I have here? Only one, the t, correct? So what do? You move one to the other side, or you can say that they equal to 0, right? So you say 0 equals, take t outside, t multiplied by 5 minus 4.9 t. Correct? Make sense? So it's either t equals to 0, which is impossible, or t equals, solve for t from the second one, which is 5 divided by 4.91. How much is 5 divided by 4.91? It's either this is 0 or all this is 0. That's fine. So move to the other side. 5 divided by 4.91. How much is that? So my time equals 1.02 seconds. So this is how much time it takes the ball to reach to the other side, to C point. Now take the time, plug it here, you get your final velocity, final distance. I used only 2 equations to solve for this projectile problem. So let me erase this and see if we are getting the same. I think we're good with these. Time 1.0 to 1.0, perfect. So that fixed, that checks. Take that time, plug it in v final x. So you remember we said we have the vcx and the vcy. The vcx is the same, right? Remember we said the velocity in the x-axis is going to be the same. Now the final velocity, we use another formula. The final velocity equals the initial velocity minus acceleration multiplied by time. Remember? But now on the y-axis, not on the x-axis. So v final of the y equals the v initial, which is 10 sine 30, minus gravity is 9.81 multiplied by the time. You now get the second component. So here, the first component, that was from the beginning. We know that this thing. This is v final, right? In the x. And this is here, the v final in the y. So he's using C as final, right? Because that's the point C here. But I like to use the final point, initial point, so that we can do it. Now I have 2 components, right? I have the vfx and vfy, the final x and y. We need to find the resultant. So how do you get the resultant? You take the square root of each one, the summation of them squared, right? because that's the resultant. So the V final, or VC, how he's calling it, is going to be the square root of 8.66 squared plus 5 squared, and that's your final velocity. So the ball will hit the ground with a velocity of 10 meters per second, right? And if you would like to find how much the distance was, you just, x final equals v is equal x initial, so x final equals x initial plus v x initial t. We don't have x initial, it's 0, right? So vx of 0 is 10 cosine multiplied by t, which is 1.09, and then you get how far the ball actually moved to the next, to the location, to the right. It's a quick review. We're going to solve multiple questions. I'm going to give you more questions to look at and see how that is going to be looking at. How we're going to solve it. Okay, now we have 10 minutes. So here's what I want to do. Any questions about this? Right. I would like from you to think about this problem. Right? And I'm going to give you pieces of paper, and let's see if we can replicate what we did on your own. And we'll upload this to D2L, and then we will discuss it and see how that's going to be. I think we're going to I'll give you 10 minutes, and I will start with this next time just to check if your work is okay. Remember here, your distance, this 150 is going to be negative 150 because you're going down. So I will set my origin, the 0 point, to be here first. That's 0 point, and then you start from there. So your y final is minus 150. Let me see if I can do it with you as well. So I will break this thing into two, right? That's x, that's y. So I will say that my vx0 equals, so that's 150, right? 150. Now, we're giving a triangle, so if you would like to find the horizontal, you divide it 4 by 5, correct? Right? So you put 4 divided by 5. So that will give you the horizontal component. Now, Vx final is the same thing. Should be the same. So that's 5, that's 1. If you divide this is 3, so that's 30, so that's 0, that's 120 meters per second. So that's the velocity in the x-axis. Now, the position in x-axis, the final position, equals the initial position plus vx0 t, right? That's the equation of motion. Now, x final is r. That's our x final. X initial is 0, because that's the 0 point. Now, Vx of 0 is 120 multiplied by t. So that's my first equation. Right? So that's the first equation of motion. Now, how many unknowns do I have? 2. We need to find another equation to solve this. So what we did there in the y-axis, what did we say? You said that y final, right, equals y initial, correct? What's the formula? So it's going to be vy0 t minus half 9.81 t squared. Here's what happened. For the vy0, how much is that? That is 150, and it's the vertical, so that's 3 over 5. correct? So that's 533, that's 90 meters per second. Now, your y final is minus 150. Do we agree? Because we went down. That's 150. So I'm hitting here, so not minus 150. Now, y initial is 0, so that's gone. Vy0, that's 90. T minus 4.91, right? T squared. Now this is my second equation. Does it make sense? Now you move the 150 to the other side, then you will have 0 equals you move it to everybody. Move these two to the other side. This one and that one, so that they're positive. So you'll have 4.91 t squared minus 90t minus 150 equals to 0. This is an equation that we can solve using your calculator, or you use a MATLAB or anything, and you get T1 and T2, correct? One of them will be negative, the other one will be positive. We use the one that's positive. Take that time, subtract it, put it here, you get the distance R that the distance travels, and you're done. Take the time from this one, because that's only one unknown, and it's a square equation, and then you plug the T here, the positive one, and then you get your R to be the distance that thing's traveling. So if we check this one here, we have, that's 120 T, that's good. Now then you do the Y 150, that's correct. You solve for T, that's 19 seconds. Plug it there, that's 2,387 meters, and that's your projectile. That's this. So we solved for a velocity and a projectile in two different examples. We are, refreshing our information about statics, but we're going to use it later on. Dynamics, but we're going to use it later on.